So let's work out an example. By the way, I should, nowadays, we're not back 50 years. The exponential matrix has the same status on, say, a MATLAB or Maple or Mathematica as the ordinary exponential function does. It's just a command you type in. You type in your matrix, and you now say exp of that matrix, and out comes the answer to as many decimal places as you want. It'll be a square matrix with entries, carefully written out. So in that sense, the fact that we can't calculate it shouldn't bother us. There are machines to do the calculations. What we're interested in is it as a theoretical tool. But let's, in order to get any feeling for this at all, we certainly have to do a few calculations. So let's do an easy one. Let's consider the system x prime equals y, y prime equals x. This is very easily done by elimination, but that's forbidden. So first of all, we write it as a matrix. So x prime, it's the system x prime equals 0, 1, 1, 0, x. So here's my A. And so e to the at is going to be, so A is 0, 1, 1, 0. So what we want to calculate is we're going to get both solutions at once by calculating at one fell swoop e to the at. Okay, e to the at equals. Okay, I'm going to actually write out these guys. Well, obviously the hard part, and the part which is normally going to prevent us from calculating this series explicitly, by hand anyway, as I say, the computer can always do it, is the value. How do we raise a matrix to a high power? You just keep multiplying and multiplying and multiplying. That looks like a rather forbidding and unpromising activity. Well, here it's easy. Let's see what happens. What is a, if that's a, what's a squared? I'm going to have to calculate that as part of the series. So that's going to be 0, 1, 1, 0 times 0, 1, 1, 0, which is, da-da. So, brr, 1, brr, 0, 0, brr, 0, 1 plus 0. We are saved. It is the identity. Now, from this point on, we don't have to do any more calculations, but I'll do them anyway, just to, what's a cubed? Don't start from scratch again. God, from 1 times 1, no, 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 no. A cubed is a squared times a, and a squared is in real life the identity. Of course, you would do all this in your head, but I'm being a good boy and writing it all out. So this is I, the identity, times a, which is a. I'll do one more. What's a to the fourth? Now, you would be tempted to say a to the fourth is a squared, which is I times I, which is I, but that would be wrong. A to the fourth is a cubed times a, which is a cubed, I've just calculated, is a times a. A cubed I just calculated was a, right? And now that is a squared, which is the identity. It's clear this is, by this argument, it's going to continue in the same way. Each time you add an a on the right-hand side, you're going to keep alternating between the identity a, the next one will be the identity, the next will be a. So the end result is that the first term of the series is simply the identity. The next term of the series is a, but it's multiplied by t. So that is 0. Should I put it, I'll keep the t on the outside. Remember, when you multiply a matrix by a scalar, that means multiply every entry by that scalar. So this is the matrix 0, t, t, 0. I'll do a couple more terms. The next term would be, well, a squared we just calculated is the identity. So that looks like this, except now I multiply every term by t squared over 2 factorial. All right, go for broke. The next one will be this, times t cubed over 3 factorial. And Fortunately, I've run out of room. Okay, let's calculate then. Maybe I should do it. Well, no, we're going to need that. Okay, let's do it here. So what's the final answer for e to the at? It is, I have an infinite series of 2 by 2 matrices. Let's look at the term in the upper left-hand corner. It's 1 plus 0 times t plus 1 times t squared over 2 factorial plus 0 times t. It's going to, in other words, be 1 plus t squared over 2 factorial plus the next term. It's not on the board, but I think you can see it's this. And it continues on in the same way. How about the lower left term? Well, that's 0 plus t plus 0 plus t cubed over 3 factorial and so on. So it's t plus t cubed over 3 factorial plus t to the 5th over 5 factorial. The other terms in the other two corners are just the same as these. This one, for example, is 0 plus t plus 0 plus t cubed over 3 factorial. And the lower one is 1 plus 0 plus t squared, and so on. So it's the same as 1 plus t squared over 2 factorial, and so on. And up here we have t plus t cubed over 3 factorial, and so on. Well, that matrix doesn't look very square, but it is. It's infinitely log physically, but it isn't. It's got one term here, one term here, one term here, one term there. Now, all we have to do is make those terms look a little better. For here, I have to rely on the culture which you may or may not possess. You would know what these series were if only they alternated their signs. If this were a negative, 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 then the top would be cosine t, and this would be sine t. But they don't. So they are the next best thing. They are what? Hyperbolics, right? The top is not cosine t, but cosh t. The bottom is sinh t. And how do we know this? Because you remember. And what if I don't remember? Well, you know now. That's why you come to class. Well, for those of you who don't, and in fact, remember the nice way to, so this is e to the t plus e to the negative t. It should be over 2, but I don't have room to put in the 2. This doesn't mean I will omit it. It just means I will put it in at the end by multiplying every entry in this matrix by 1/2. So if you've forgotten what cosh t is, it's e to the t plus e to the negative t divided by 2, and the similar thing for sinh t. So there is your first explicit exponential matrix calculated according to the definition. And what we have found is the solution to the system, x prime equals y, y prime equals x. A fundamental matrix, in other words, are cosh t and sinh t satisfy both of those, are both solutions to that system.